In this next series of videos, I want to talk about frequency responses. Now, the frequency response of a circuit is a description of how the output of the circuit varies as a function of frequency. We've already seen that some components, notably capacitors and inductors, have impedances which are a function of frequency. And this means that any circuit built with inductors or capacitors tends to have an output whose amplitude or phase will vary with frequency as well. I'll try to stick to these definitions. The amplitude response of a circuit describes how the gain of that circuit varies with frequency. That's just the amplitude gain. The amplitude of the output divided by the amplitude of the input as a function of frequency. The phase response of a circuit describes how the difference in phase between the input and the output of a circuit varies with frequency. The frequency response is a combination of both of these things. It contains information both about the amplitude response, the gain as a function of frequency, and the phase response. We can consider this simple circuit as an example. Single resistor, single capacitor. It has the form of a potential divider, so we can use phasor analysis and write the output phasor representation in terms of the input phasor representation, just using the standard potential divider equation. And what we would get is the output voltage, or the phasor representation of the output voltage, is equal to the phasor representation of the input for voltage times 1 over j omega c over r plus 1 over j omega c, noting that the complex impedance of a capacitor is 1 over j omega c. The gain of the circuit, I'll usually write this as h of omega because it's a function of frequency, is the output phasor divided by the input phasor representations, and that, if I multiply up both top and bottom of this expression by j omega c, it gives me the simple form 1 over 1 plus j omega rc. And that is an expression which contains information both about the phase change of the circuit as a function of frequency and the amplitude change of the circuit as a function of frequency. I could write h of omega in the general case as a amplitude response. I'll call it a of omega, and that's going to be a real number, a real function, times e to the power of j, and then a phase response. I'll call it theta, function of omega, so that a is the magnitude of h of omega at any particular frequency, and theta is the phase angle of h of omega at any particular frequency. Then I would have that V out is equal to a of omega times e to the j theta of omega times V in. And V out and V in are both phasors. A and theta are both real functions, functions that take in the frequency and give you a real number as their output, the amplitude gain and the phase change. If I expressed V out, the phasor V out, as the magnitude of V out times the phase of V out, theta out in this case, a of omega e to the j theta of omega, and do a similar thing with V in, express the amplitude of V in as modulus of V in and the phase of V in, e to the theta in, I could rewrite the right-hand side of this equation as a of omega times the modulus of V in. That's two real quantities multiplied together, giving me a real quantity, e to the j theta omega plus theta in. That's a real angle. This is a real function. That equals modulus of V out e to the j theta out. Comparing the magnitude of the left-hand side to the magnitude of the right-hand side, we can see that the modulus of V out equals A of omega times the modulus of V in, or in other words, modulus of V out divided by the modulus of V in equals A of omega. A is, in other words, the amplitude response. It's the ratio of the magnitude of the output to the magnitude of the input as a function of frequency. And if I compare the phase of the right-hand side to the phase of the left-hand side in this equation, I would see that the phase of the output is equal to the phase of the input plus theta omega, which is the phase term in the frequency response up here. So in other words, theta omega equals theta out minus theta in. It's the difference in phase between the output and the input. In other words, the phase response. And combining the phase response with the amplitude response in this way gives me what I will refer to as the frequency response. We can investigate this kind of circuit in the simulator. We'd see something like this when I put the simulator into AC analysis mode. You'll see that the phasor diagram here, this is an Argand diagram with the phasors written on it. The phasor of the input is just 1 volt at a phase angle of 0, so that corresponds to the real number 1. It appears there. The phasor of the output is at minus 45 degrees at this particular frequency, and a magnitude of about 1 over root 2 volts, and that appears down there. So at this particular frequency of 159.06 Hertz, the magnitude of the output is about 1 over root 2 volts. The phasor appears there, and the difference between the phase of the input and the output is about 45 degrees. It's minus 45 degrees. That's why it's shown down here on the phasor diagram. And you'll see that the output is lagging the input. The input goes through its maximum before the output goes through its maximum. The input rises through 0 before the output rises through 0. So the output is 45 degrees behind the phase of the input, and we notate that by writing its phase angle as minus 45 degrees. You can ask the simulator to plot frequency responses as well. If we have a look at the menus, go into Sim Controls and head over to frequency responses, then you'll see that, actually we'll turn that off for now, you'll see that the frequency response of the output here is plotted on a scale of dBV against a logarithmic scale of frequency. And we'll talk about why we tend to plot on a dB scale against the log of frequency in a following video. This, of course, is just the amplitude response, though. You can show the phase response as well by just clicking the control there, and you'll see the phase response here starts off at 0 degrees, and as the frequency increases, heads down to about minus 90 degrees. You can, by the way, pick up this grey line, which shows where the current frequency is, and move it around if you want to see the performance of the circuit at different frequencies. You may have noticed in that previous slide that the plot had a roughly horizontal line at very low frequencies, and again it had a straight line at higher frequencies. And this only happens if we plot dBs on the y-axis against a logarithmic scale of frequency on the x-axis. But assuming that we've done this, we can extrapolate that high frequency straight line to where it meets the low frequency straight line, and where those 2 points meet is called the break frequency, or sometimes the corner frequency. And that's an important parameter that we'll be returning to later. That's all for this first introduction video. Next time we'll be having a look at how to analyse the performance of the RC circuit in a bit more detail, and exactly why we tend to use a dB scale on the y-axis and a logarithmic frequency scale on the x-axis.